So my talk will be having a slightly different flavor. I am from academia and I'm a structural engineer, unlike I believe most of you are mechanical or electrical engineers. So the title of my talk is Finite Element Model Updating and Condition Assessment of Existing Structures. Okay, the way I have organized the talk is I will just provide the motivations for this topic, and I will spend some time on issues that arise when we deal with existing structures which are instrumented, and then question of model updating, what it means, and some applications. This subject of model updating has gained importance in structural engineering because of emergence of this new methodology called structural health monitoring. So what this is, a moment a structure comes into existence, many clocks begin, like fatigue, corrosion, and application of the design loads and so on and so forth. So the intrinsic property of the structure goes on changing with time, and that creates changes in the mechanical properties like mass, stiffness, and damping characteristics, because of which the signatures of vibrations like strains, displacement, velocities, etc. will depart from what they would have been when the structure was in its virgin state. So now the job is to extract the features from these measured signals and identify the damages, if any, and then we have to say where is the damage, what type of damage, how much is the damage, what is the residual life, and we should take decisions on repair and retrofit. So the idea is at its best, it should be a completely automated procedure with little of manual intervention. So there are now very large scale systems which have been instrumented. For example, this is the one of the bridges with more than about 1700 sensors which gather data around the clock, 24/7, 365 days. It has things like measuring wind velocities, acceleration, temperature, so on and so forth, that is listed there. So now this provides huge amount of information on the what is happening to the system, and if this bridge is going to fail in next 10 days, during the intervening 10 days it will give us sufficient warnings through these signals that something is going wrong. So our talent lies in identifying them and taking corrective steps. So this is a famous failure that was observed in Montreal. This is a bridge where one of these slabs simply collapsed one afternoon, and the interesting thing was this bridge was inspected a few days before and everything was declared fine, and without any warning this slab collapsed and there were deaths and things like that. So then the question of how reliable is the manual inspection of these structures gained importance, and this is one of the incidents which kind of makes a case for sensor based monitoring. Now on a slightly different line, there are what are known as digital twins that are being developed for space vehicles. See, the idea here is in a space vehicle, as and how the mission time progresses, the sensors, the structure would be instrumented and there will be a continuous gathering of data on what is happening to different parts of the structure, and on the vehicle there will be a finite element code which keeps on getting updated with based on the measurement that arrive, and that finite element code essentially creates some kind of self-awareness to the system, and that in fact becomes a virtual fleet leader. If it is an unmanned mission taking going for months, so you create a twin for the system which is computational. So this is another idea which is being explored. Now in the area of structural engineering, this subject has been over the last decade or so, there have been many studies. So I have just put a collage of some of the important publications that are available. So this material will be available to you so you can see that. Now the focus of my talk is on existing civil engineering structures. Now civil engineering structures are large sized and large volume of material will be used, unlike any machine or any other motor, generator and things like that was being talked in the morning. Here volume of material that will be used is enormous, like a dam or a nuclear reactor or a multi-story building, the amount of material that is used is large, and that means there is a greater scope for occurrence of defects and so on and so forth. And initial expenses for civil engineering structure dominate the cost. Unlike aircraft and automotive systems, maybe about 95% of the total cost is spent in the initial stages. So one may question whether structural health monitoring is really going to take off for civil engineering structures. Now, there are prescriptive practices. Civil engineering design proceeds based on codes of practices, and is a highly regimented activity. So that is one other aspect of this. And there is a great deal of room for visual inspections and personal judgments on monitoring existing systems. Now, one more thing that I could have included here is no two civil engineering structures will be alike. They are not mass produced, right? So they are constructed facilities. So no two dams are alike, no two houses are alike, so on and so forth. So it's a case-by-case problem that has to be tackled. Now, when a structure comes into existence, before a structure comes into existence, we base all our designs on a mathematical model. But once it comes into existence, we have the opportunity to measure how the structure is performing, right? So that means unless you measure how a structure is performing after it comes into existence, it makes no difference to us. If you don't measure what is happening to the structure, it's almost like as if it hasn't yet come into existence as far as managing that system is concerned. So you still have to rely on the mathematical model. Now, on the other hand, if you can instrument the system and monitor how it is performing, then the question of we can bank all our judgments purely based on measurements or purely based on mathematical models, or a better option would be to combine the might of these two approaches. So this is the question. Now, of course, the enabling technologies, computational and sensing technologies which have emerged, and this has made this type of approaches feasible. Now, a bit of mathematics. So you can skip, you need not have to look at these equations. The point I will briefly say what I wish to say here. If a structure hasn't yet come into existence, we bank on laws of mechanics and set up the governing equation for equilibrium and so on and so forth. And based on that, we compute stresses, strains, displacements, and other things based on which we take decisions. It could be on reliability, it could be on a design format, it could involve sensitivity calculations, so on and so forth. Now, the tools that we use is finite element methods, Monte Carlo simulations, optimization methods, so on and so forth. Now, once the structure comes into existence, measurements become possible. So what happens to all the models that you developed? Basic FE model, the model for reliability, the model for sensitivity, other things that you would have modeled when you were designing, all those models can be revisited. So this process is known as model updating. That is, you have to revisit your model and see, since you are now measuring the response, how you can assimilate the measurements into your mathematical models. Now, so we can pose some of the questions. Suppose you have an instrumented system, you are measuring displacement, stresses, strains at few places. You can't measure all the response features that is of interest to you because there are so many hidden variables and so on and so forth. For example, state of stress inside somewhere in a critical section, it may not be accessible for measurement. So what we do is, the first problem that we consider is, how do you estimate what is not measured based on what has been measured? So what we do is, we make a mathematical model for the system, and we predict what has been measured, and obviously that won't match with what hasn't been actually measured, and there is an error metric. In some sense, we want to minimize that with respect to some of the parameters. It broadly proceeds on that line, and this is a problem of estimation of hidden states. If you could succeed in doing that, then this mathematical model, which has assimilated all the measurements that is available, becomes like a virtual sensor. What has been measured is incorporated into this. What has not been measured comes out of a mathematical model. So the mathematical model virtually becomes like an infinite source of information, as if you are actually measuring responses wherever you want. On the other hand, there are problems of system identification. That means parameters of the system themselves are not known. So what we do is, suppose we apply known excitations and measure the response, and we want to identify the parameters of the system. That problem is known as problem of system identification. Now, to deal with that, we write the governing equation, which is our usual FE-based model, and this is what is the sensor-driven measurement model. Now, I will come to some of these details slightly later. The thing is, we want to know theta are the system parameters. It could be damping, elastic constant, there are many other things of interest in mechanical modeling. And I want to know what is the probability density of these parameters after I have made measurements. Now, I have used the word probability density function, so I have to say why I am doing that. I will come to that. Now, here there are two types of problems that one can think of. One is changes in the operating environment. Right, for example, a railway bridge may carry higher loads, or a faster train or a locomotion technology may change, or if you look at earthquakes, the perception of the risk may change. I will come to that. So then I have to take a decision on whether the structure, we can continue to use the structure as it is, or does it require any retrofit or any other additional measures. So then while doing that problem, I need to know what is the current status of the system, and that is condition assessment. It is episodic in time. Sometime I will do it. Whereas in health monitoring, we continuously monitor the response of the system. And as and how the changes occur, I will also be changing my model. So it is a continuous process. So condition assessment is a much simpler problem. So my talk is mostly on condition assessment. Now if you come to some statistics, this is number of bridges in Indian Railways. So you can see here, the first column here gives year of construction and the number of structures. So you see roughly about 45% of the bridges have crossed 100 years of service life. But still they are there. Every day our trains pass on them, free traffic passes on them, and the meter gauge becomes broad gauge, steam engine becomes diesel engine becomes electric motor, this thing, the fleet length increases, speed increases. All the changes are taking place, but the structure remains the same. So now the question is, these are all aging infrastructure, and what do you do with them? How do you maintain them? So you need scientific inputs for that, right? So this one can call it as structural geriatrics. Okay, it's like looking after aged population. How do you do that? Now, we were involved in one project for Indian Railways, where the line from Hospet to Goa, which carries iron ore, they wanted to increase the axle load from 20.8 tons to 25 tons. So the question was, what decisions have to be made based on, pertaining to existing bridges. So they identified 5 bridges. Some of these are iconic, that is the Dudhsagar bridge, and some 2 plate girder bridges, 1 stone masonry, 1 brick masonry, and a lattice girder bridge. They identified, and the problem was, can increased loads be applied on these bridges or not? Now, we were not permitted to apply the enhanced loads because they are all live bridges. So what we did was, we applied certain test loading patterns on the bridges, moving vehicles, accelerating speed, braking on the bridge, and so on and so forth, and we collected the response of the bridge, dynamic response, based on which we updated the finite element model for these bridges, and then on the updated finite element model, we applied the increased axle loads and other enhanced loading issues, and predicted how the structure might behave. Right, so these bridges, there are no original drawings, and we don't even know which material was used, and whether, for example, for this brick masonry bridge, what we were told was, where from those bricks came itself was not known. Was it brought from Portugal, or it was actually constructed by Portuguese engineers, not Britishers, because it was in Goa region. So it's too complicated, right? So we have to go and actually take measurements, make drawings. So everything has to be done from scratch, right? So it's a complex task. Now the another issue, this again pertains to change in loading patterns. The another thing is earthquake loads. That see, these are the zonation maps that has evolved over last few decades from 1962 to the current zonation map. So as our experience with observed earthquakes accumulated, our perception of risk has also changed, right? So what was considered as zone 1 in 1962 maybe in some other zone now, right? But today there are many structures which were constructed in 1962, which were constructed in 66, which were constructed in 1970. Actually nothing has been done to them. See, today if I construct a structure based on that design, it won't pass through the codal requirements. right? So there is a problem that society has to deal with. We are not addressing that problem. But if you have to address that problem, how will you go about scientifically doing that? How will you prioritize existing structures which need retrofitting and say what is the deficit of retrofit that is to be made to bring it up to this? How will you prioritize? So all these requires, answers to very complex questions. I was reading this book by Atul Gawande. He is a medical doctor at Harvard. So he has written a book called Being Mortal. It's about human beings, obviously. So there, one graph caught my attention. So there is a measure of well-being, and you're doing well, and your health deteriorates, and you die. But you are given medical attention. So as your health deteriorates, you receive medical attention, and it's not a sudden drop, right? So now there is one more paper on maintenance of civil infrastructure. So you can see there is a nice correlation here. This is reliability, and with no maintenance, the reliability drops and the structure dies at that point. Whereas if you have maintenance, you repair, strengthen, do everything. So it almost looks like this. Okay, so I'm told that in US, an average American goes through about 8 to 10 major medical procedures during a lifetime. Okay, so I don't know what is the statistic in India. Now here we have, when we talk about existing systems, we have data from experiments, data from mathematical model. Which will you trust more? Experiments, right? That's what we tend to believe. Now, there's a famous saying, I think it's attributed to Einstein. If I do an experiment and say this is how it is, something is happening, everybody will believe what I'm saying, but I will have lots of doubts on what I'm saying. But if I develop a theory and say this is what is going to happen, everybody will suspect what I'm saying, but I will be very sure of what I am saying. Okay, so there is a problem here. So let's see what happens. See, this is a figure from the well-known finite element analysis book by Cook and Malkus. So there is one example here. There is a simple, one-span beam subjected to a transient pressure load. And you are supposed to do a nonlinear analysis, nonlinear transient dynamic analysis, and predict, I think, the time history of mid-span displacement or strain, displacement. So these results that you see here are obtained by using different finite element packages by different people. So you can see here nobody agrees. Suppose if I say what is the answer after 2 seconds, right? The answer varies from this to that. Okay, this is all, any one of us could have done one of these graphs. Okay, right. Now therefore there's a problem. Now how about validating through an experiment? So this was an experiment that was done out next door CPRI. There was a 4-story building which was pulled by winches till it brought to certain collapse condition and near collapse. So the problem was all this design was made available to people before the experiment was done, and people were invited to submit a graph of what will be the basically the load deflection diagram for this. So you see here there are I think about 12 or 15 people who have participated in that exercise, and this dark line is the actual experiment. Whereas these are the results predicted by experts, not students, right, from IITs and reputed labs. So again here you can see the load required to produce 200 mm displacement according to model can vary from this, which is some 400 kilonewton to something like 1600 kilonewton. Now we are basing all our design on such models, okay? But whereas experiment shows something else. Now how about experiment itself? Now this is another study done by Imperial College London. Some 4 machine elements were circulated in Europe, I think to about 25 labs, and everybody was asked to measure transfer function between 2 points. Drive here, measure here, do whatever you want. In the sense, whichever method you want. It is in free condition. You have to decide how to suspend it, and you can use impulse hammer or you can use model shaker, do whatever you want. And the same specimen was transported from one lab to the other. So these are what you see there is the ensemble of frequency response functions reported by experts. So it showed about 8% fluctuation in first natural frequency, much more at higher modes, and about 225% variation in damping. This is done through experiments. Okay, so what is the moral? The moral is there are errors in FEM, there are errors in experiments, and what we need to do is if you are going to combine the two, you need to recognize the fact that neither of them is perfect. So in one model updating method known as Bayesian model updating, we model these imperfections probabilistically, okay, and update the models. So that is one approach. The other approach is method of inverse sensitivity analysis. So I will first say a few things about inverse sensitivity analysis. So what you do here is, let P1, P2, P3, Pn be some generic parameters, like parameters associated with loss of stiffness at different places, or damping, or some other flexibility at joints, and so on and so forth. Now you find out certain response features like natural frequencies, it could be some global measures of system performance, things like that, and these are all functions of these parameters. Now in the healthy state, they will have some reference values, and as the structure changes, all these response features will undergo a change. So you do a simple Taylor series expansion and compute the changes, okay, the gradients. Then you will get an equation like this. This is a change in observed system parameters. This is a sensitivity matrix, and this is changes in the system parameters. This is change in the observation, like natural frequency, mode shapes, etc. Then we find out these changes, which help us to identify how the model should be updated using a kind of a pseudo-inverse approach. So this is a broad principle of, it's basically application of Taylor series, first order Taylor series or higher order improvement to that. It results in not a well-posed set of equation. You have to use regularization, singular value decomposition, and a slightly different type of mathematics, but it can be done. Now I'll skip this. But this method, the problem is, it is very sensitive to the imperfection that I was talking about. We worked on both these methods, and even a cantilever beam humbled us. You see, you take a cantilever beam and put some masses and take the measurements and remove the masses and redo the measurements, and you have something like a damaged system, right? And try to see what changes you have made. Can you work backwards and get them? Even in such antiseptic, clean environment, it was very difficult, because these inverse sensitivity methods are very unforgiving to small errors. Okay, you have to take care of many issues. So what we found was probabilistic methods are best suited for this. So Bayes was a priest in Scotland, and he wrote a kind of an essay on a treatment of uncertainties, and the so-called Bayes theorem was contained in that. And after he died, his friend published it. So Bayes doesn't know that there is a theorem after his name. So the Bayes theorem actually is a very nice philosophical thing. It helps us to deal with situation where there is a mathematical model and there is an experiment. See, those of you who are students, either you do research in experiments or either do in analysis. And then if you are doing experiments, you will somehow try to compare with some analysis. If you are doing analysis, you will take somebody's experiment and try to show what you are doing is reasonable. But you can use both the methods in a single framework, right? That what Bayes theorem says. I will not get into the mathematics. It is, it takes some effort, but it is accessible. So I will skip that. What Bayes method also does is, you see, when I am talking about system identification, I have a model in my mind. But how about model identification? Who will tell that? For example, there is a beam. One of you may model it as Euler-Bernoulli beam. I may model it as Timoshenko beam. Somebody may model it as an anisotropic, three-dimensional solid undergoing geometric and material nonlinear behavior, so on and so forth. So, who will select the model? If you select one model, you can do system identification. But what is needed actually is a model and a parameter identification, right? So Bayes method provides for that. A more detailed model is not necessarily the best model. For example, if you have 1 lakh data points, you can fit a 1 lakh order polynomial and force your fit to pass through all the data points. Okay? But y equal to mx plus c may not pass through any of those data points, but may be the best fit. So there is a question of parsimony. That is, you should penalize a over-fitted model and honor the accuracy that is required. I mean, it is realized. So Bayes theorem allows for these kind of things, and one can do that. Now, this subject falls into the area of what is known as data assimilation. It is used in weather prediction and many other branches of science. So in the context of health monitoring, it's almost like weather prediction. How is the structure going to behave if this is how it is behaving right now? And you have, instead of Navier-Stokes and other equation, you have actually your solid mechanics and other equation. So it's roughly the same, right? But the issues are quite different. So there are two important things that I want to highlight. Again, I cannot get into the details. That there are two major computational tools known as Markov chain Monte Carlo and Monte Carlo filters. They are all basically tools for handling integrals and things like that, which appear in this calculation. And if you combine this with finite element method, then you have the most potent modeling tool. At least in my opinion, it is the best tool that one can think of for modeling, because it incorporates FEM and all that FEM can do, and it also takes into account all the data that you get, not only from strain gauges and accelerometer and things like that, even from NDT. Even expert judgments can be built into this, right? So it provides a single framework. So those youngsters among you who want to do research, this is one area where there's a lot that can be done, okay? So there are issues, I will again not get into this. So I will talk about few things that we did for Indian Railways. So, yeah, so these are the suite of the bridges that we studied. Can you go back to the previous slide? It shows the sensor layout on that bridge. So there are accelerometers, there are strain gauges, there are tilt meters, temperature gauges. We had a 96 channel data acquisition system, and the deal was on every bridge site we will collect data for 100 hours. During that 100-hour window, whatever ambient traffic that passes, we'll have records of all that, right? And in addition to that, we formed certain test formations. I think next, this one. See, this is an engine followed by two wagons which carry some enhanced load, and there are certain open web girders where we placed different number of sleepers. Each sleeper, prestressed concrete sleeper, weighs about 300 kg or so. So by varying their number, I know what weight I am putting on them. And we made this special train. We designed this formation to crawl on the bridge, run with different speeds from left to right to left, brake, stop and run. So many things we did. So we have a wealth of data on these 5 bridges. And we're still trying to use all of them. I don't think I'll be able to use all of that. Maybe we would have used by now about 15% of the data that we have actually collected, right? So we did impulse response test. This is an instrumented sledgehammer. You might have seen the instrumented impulse hammer that you use in laboratories. This is an instrumented sledgehammer which can be used to measure FRFs of large-scale systems. Okay, so the basic philosophy was we made a FE model, we had a database of measurements, and we wrote a suite of programs on MATLAB platform which incorporated the arguments that are encapsulated in the Bayes theorem. Okay, and that is computationally very intensive. So we made all these three to talk to each other, and this involved, a kind of flowchart like this. We did several tests on the bridge structure, like a static load test, motion with constant velocity, accelerating, braking, and all that. Each one we simulated on our FE package, and the predictions from each of those simulation run was compared with the corresponding measurement, and that won't agree. I mean, it will never agree. So how do you, next what you do, you have to, and both are error prone. So you have to probabilistically correct that and get a better estimate of the system state and the parameters. So these are broadly the outlook. There are a lot of computational details. We could do that, and we used we started with a 3-dimensional FE model for this and settled down to a plane stress model, 2-dimensional, about 2000 degrees of freedom with about 76 unknowns. And actual data collected from the field work was used in this model updating. So to me, it appears it's one of the largest problems that has been solved in the area of finite element model updating, as far as I know. So then we got some, initially we started with some initial guesses, and as our iterations proceeded, the predictions from model and the measurements started agreeing on some kind of a global sense. And also what we did was we kept aside some measurements for sake of validating, which was not used in system identification, and those data was used to verify whether after identifying the model, how good is my model. So this has worked out well. All this has been published and taken measurements from that. How do you combine the two? That's the basic question. So that can be based on a deterministic approach or probabilistic approach. As I already said, deterministic approaches don't fare very well, at least for the data set that we worked with. Unless you model the uncertainties, things don't work well. So thanks for your time.
For this Bayes theorem, how much data is enough data if we are doing experiment? And when you are working with a structure, it would be like you have lots of money. But when we are in an industry, every day we are changing our configuration and everything. So how much it would be valid for us?
That's not an easy question to answer because the question on identifiability of systems mathematically has not been settled. There is no clear answer that if you do this much measurement, you will get the right answer. But having said that, it is slightly iterative. In all engineering, there will be some iteration. You start with some, then you can decide upon whether you are actually overdoing it or underdoing it. There are ways of getting a figure of merit for a particular configuration of measurements, and that you can assess. Suppose there are even sensor placement also is an issue. It's not just the amount of measurements. See, the problem with in inverse problem, the solutions are not unique. Less measurement means there are more possible answers. That's the danger, right? So one can say that we can live with that, because suppose if you find non-unique solutions, it only means you have to inspect more. But it at least tells you where to inspect, right? But a clear-cut answer to this is not possible.
So when you build mathematical models, stiffness and mass to a good extent can be estimated. But what about the damping? Because damping depends on the structural damping, especially depends on the shape, direction, and everything, and also function of load and time. So what is the best practice that you follow?
Oh no, these are very difficult questions, but I would also contest whether you can really evaluate stiffness correctly. Simply because boundary conditions, boundary conditions and other things, even natural frequencies are not. I showed you some simulations, experimental simulations, where natural frequencies are also not found out correctly, leave alone damping. Right. Damping shows high variability. So my approach would be, you respect that there is variability and get an answer in probabilistic terms. Okay. Then you know this much confidence you can have on your answer. But if you say damping is 0.1%, and you don't have any confidence band on that, that's a very poor answer. The Bayesian method tells you it is not 0.1, but its distribution is this. So you do whatever engineering decision, that is more information.
It was great and wonderful. Dr. Manohar brought down the complex concepts for all of us to make understand, also give very valid engineering comments. Thank you.
My pleasure. Thank you.